Hello, everybody. Welcome to the Global Composite Experts webinar series. My name is Wenbin Yu, the Director of Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites, with the goal of sharing the knowledge of composites that has been developed over the past 5 decades. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We launched the Composite Design and Manufacturing Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. And CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We expect CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives we have started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors. The current sponsors include Dassault Systems, Cytec Solvay Group, and Anna Swift. We greatly appreciate their financial support for CDM Hub. We invite more organizations to join us to serve the global composite community together. This webinar will be recorded and made available on cdmhub.org. We will email you once the recorded video is available online. The presentation will last about 40 minutes, and we will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the presentation, your questions will be read and answered. Next, let me ask Professor Dianren Zhang to introduce our distinguished speaker today.
Welcome, everyone. My name is Dianren Zhang. I'm an assistant professor of the School of Aeronautics and Astronautics at Purdue University. Today, I'm honored to have the privilege to introduce our webinar speaker, Professor Karl Schulte. Professor Karl Schulte is editor-in-chief of the international journal Composite Science and Technology, and had been professor and the head of the Institute of Polymer and Composites of the Technical University Hamburg, Germany, until 2013. His research focused on degradation of fiber-reinforced composite materials, nanocomposites, and the synthesis of carbon nanotubes and aerographics. Professor Schulte is member of the editorial boards of several national and international journals in the area of composite materials. Together with his collaborators, he has published more than 300 peer-reviewed publications in journals, books, and conference proceedings. ISIHighlyCited.com listed Professor Schulte as highly cited researcher in material science. Based on Scopus, the number of his citations amount to 20,460 as of today, and his high edge index is 66. He is elected by Fellow of the Churchill College of Cambridge, UK in 2013. In 2013, the International Committee for Composite Materials named him Composites World Fellow, and in 2014, he received the Medal of Excellence in Composite Materials from the University of Delaware. In 2013, he was also nominated in Germany for the prestigious Diesel Medal. After his retirement, Professor Schulte continues to work scientifically in the composites field as a consultant and assessor, and as editor-in-chief of the high-impact journal Composite Science and Technology. Now I will give it to Professor Karl Schulte.
Okay, so thank you very much indeed for the nice introduction. And okay, I will start now with my presentation. Let's see that I do not make a mistake, because I have still you in the front here, and my own presentation is in the back. So let's see what I can do. Now it goes. It's everything still fine with you? No response? Can I start my presentation?
Still seeing the video screens as opposed to your presentation.
Okay, you see the presentation now?
Not yet.
Not yet, because that had been seen. That was said. I have put it on now. I see it fine, but not you. So I exit here. Maybe we have to start it again. So.
Professor Schulte, are you sharing, have you selected in the Zoom menu to share your screen?
I did that.
Okay.
But I don't know, but because we trained it before. Now there is now a circle in it.
Hold on just a moment, everyone. We'll restart this and try getting it going again. There we are.
So I have you. You should see me. Mm-hmm.
There it is.
Can you see it now?
Yes.
Okay. And it's now okay?
Perfect.
Okay, then it's good. Then I can start. Sorry, all the attendees that we had this trouble. So again, thank you very much for the kind introduction. And going into my presentation, I have a quite global title, Composite Materials, Where We Are, Where to Go. Okay, that is in about the sense of that, what I've just have heard, that Purdue University is also want to do, goes into more a global view on composite materials. I will focus a little bit more on mechanical and also on electrical properties of polymer composites, and I will also focus on mainly carbon-based composite materials. And if we talk about composite materials, then composite materials is also and means always a research over dimensions. So that means if we want to design the nice aircraft with a wonderful structure, then we can do that only if we have a precise understanding of the material we use. And that starts from the nano level. That means from an understanding of the matrix, the interaction of the matrix with probably nanofillers, which I will talk about. We need to understand what is going on in the micro level, macro level. That means we have to do testing, coupon tests before we go to part test, and then can go further into a final structure. Over this dimension, we have to understand the material. So that means we also have, when we want to understand the material, and we are in modern design, then we need to model the material. So we have made in the past quite some progress in the modeling of materials, starting from the interaction between, for instance, the nanomaterial with the matrix, what you see in on the left-hand side, and then we go to atomistic continuum coupling models. We go into the micro scale and into the mesoscale with the coupons, and further, of course, we go into the large structure, as you see here an example of a wind turbine blade, and that means we go from the nano to the macro level for understanding and description. Now I want to go a bit into the some results, what's going on. And you see here an example on the left-hand side where we see the fibers and the matrix, the gray part of it, and inside schematically carbon nanotubes, or for instance, graphene or graphene oxide, as you can see here as well. In the past. Okay, we have our fibers, our carbon fibers, and for all of that, and we want to understand the material properties, we need to understand entirely the material. We need to know how a carbon fiber is structured, what the properties are, the tensile and the compression properties. But if we have nanofillers, we have to know also the properties of the nanofillers. We have to know the interaction between the matrix, the polymer, and the nanofillers or the part. So I will talk about nanofillers in that sense that I will use graphene or carbon nanotube, and in a larger extent, the reduced graphene must be an N here, oxide, so thermally reduced graphene oxide. And that is a material that we can put into the matrix. I will further talk about a three-dimensionally structured graphite, and we have called it aerographite. This is a hierarchical carbon nanomaterial formed in a three-dimensional network, which is interconnected and extremely light in weight. If we have more time, then I will talk a little bit more at the very end, but I will include a little bit of this into my presentation. So going back to a carbon material, and first I will talk here about just the matrix filled with carbon nanotubes or graphene oxide. Then we can see, as it is an important point, is the damage behavior in a composite material. Fiber reinforced composites might, if they are overloaded, lead to a matrix failure. Matrix failure means a crack in the matrix, probably a crack between fibers. And if we use now as a filler in the matrix carbon nanotubes, in this case it is shown, then we know from a test where we use a neat matrix, and we have added into the matrix only a very small amount of just 0.8% carbon nanotubes. There can be different types of it. I'll show that later. But what we can see is that we have an increase of a certain amount in the fracture toughness of the matrix. This increase in the fracture toughness of the matrix is due to the mechanism that we have at the very crack tip, crack deflection. We can have crack bridging, or we can, in the case of the carbon nanotube, for instance, a pull out of the nanofibers from the matrix. That results is in this increase in the fracture toughness. I have plotted here another figure, increase of the fracture toughness, K and C values versus the nanofiller content, and we use different types of carbon nanotubes, multiple wall carbon nanotubes, but also graphene nanoplatelets, thermally reduced graphene oxide as well, as you can see here. And with only about 0.5% of the fillers, we see that we have an increase in the fracture toughness of up to 40%. So this increase in the matrix properties should also result in improved properties in a fiber reinforced epoxy. So that means this is again the picture we have seen. We know it very well. And we have here just a picture with a glass fiber and a matrix, epoxy matrix. And here you see these black things here and here. All that shows that we have in the matrix carbon nanotubes, and they are in between the fibers. If we now make a compression after impact test with a composite materials, in this case a glass fiber, we have at other places also tests which show similar results with carbon fibers, then you can see if we just have a neat resin in as a matrix for the glass fiber composite, then we have this amount, and we have an increase in the compression after impact strengths of about 55% if we have carbon nanotubes in the matrix, or in this case, no, we have not carbon nanotubes. Here we have the thermally reduced graphite oxide in the matrix. And you see, this is a tremendous increase. And that means also that in further tests, this suppresses the formation of cracks. It helps, for instance, if we have a car, for instance, just an example, where we have crash elements in a frame induced, you know that from race cars as well. And if we have these types and improved material in it, then we have a strong increase in the crash resistance of a material. We know that composite materials can also have fatigue damage. And therefore, it is interesting to know if we also have an improvement, if we have carbon nanomaterials into the matrix in the fatigue results. Here we have plotted the maximum stress in a load cycle versus the number of cycles to failure. And what we can see, this is a test with fiber reinforced material without any nanoparticles in the matrix. If we add nanoparticles to the matrix, then we see here we have an improvement in fatigue life. We can have another view to this material, and then we can see what happens. I'll show later another figure where we have test results. So if we say we have damage in a composite material, then we have, due to the damage, we can translate that into degradation. The degradation we can take from a reduction in the stiffness reduction. During a damage development, the reduction in the stiffness or this degradation is due to the fact that we have damage, we have cracks, we have a transfer of the load away from the damaged area into the intact area. That means the intact area is higher loaded. We have there a higher strain, and that means we have a reduction in the stiffness, or we have then, and that is put here together, the degradation. And if we look to the degradation, then it's well known. Then we have about 3 parts, an initial part, then for most of the fatigue life, a third part, and then those two, this leads to final failure. If we now have modified the matrix with a nanomaterial, nanomodified, then we see a shift as well, that the degradation is delayed. That means this shift. And with this delay in the degradation, we have also an increase in fatigue life before we have final failure. And this we can now show in a test from various composite materials with the carbon fibers T300. You might know this is, here is an epoxy system. We have here the black line, that is the unmodified matrix. The red one, we have put 0.8% of multiple wall carbon nanotubes into the matrix, and we have a few layer graphene, something as thermally reduced graphene in the matrix. And then you can see when we change from unmodified to modified, we have an increase in fatigue life, and also the degradation is better. We have a higher degradation here when it is unmodified. And what we can even see is that we have, from the move from carbon nanotubes to graphene, we have a further increase in fatigue life. And I think this is good news. And this is something which would help in the design of composite materials for instance, aircraft. Higher fatigue life means and translates at the end also of weight saving. So the process behind that, if we have this few layer graphene, is that we not only have bifurcation of a crack and of a crack tip, but with a few layer graphene, they separate they open here and they form then either what we can see here, plastic voids, or you can also say they form here additional cracks and bifurcations. So you have inside a lot of cracks. And if you have these cracks, then it means at each cracks you have a reduction of the stress intensity factor, and that gives you a better performance in the damage developments. And that is shown here with the fibers in here. And then you see here are the few layer graphene particles, and their form in between more cracks. And that is the result why we have an improvement. If we use that, for instance, and that is used for technical products, then it is important, for instance, not only for aircraft, but we have to use to other things, to tennis rackets, or to, which is very important, a motor helmet, and something which is underestimated. That means for bicycles and bicycle frames. People think, ordinary people think, that bicycle frames are stiff and strong and you can just throw them away, but that's not the case. They are composite materials, and if you have a touch against the frame, and that means a touch against the carbon fiber tubes, then you form their delaminations. You don't see that outside. And then you use your bicycle. Maybe you go into a very difficult track and your bicycle can fall apart. So that is something to underestimate. It's mainly important to have that for the hobby cyclists. They have quite a lot of accidents on this case. So if you have a bicycle with a carbon frame, be very careful and don't let it fall down against a stone or something like that. But you see, fracture toughness is very important. The other thing is with the motor helmet, there it is very important that you have a later a damage, a higher fracture toughness, maybe also fire resistance and other things. Okay, now I want to move to electrical properties in epoxy polymers and also fiber composites. And if we go back to the electrical properties of a neat epoxy. So if I just have here the epoxy, and then I have here in the matrix distributed our nanoparticles, then, and we look to the electrical conductivity, then we can see here, if we plot here, the volume fraction of nanoparticle inside the matrix. And we have here a very good example of that, what we call percolation. Percolation means that we have very few nanoparticles in a matrix. They do not touch each other, therefore no electrical conductivity. And suddenly, if we reach a certain amount of well-distributed nanoparticles, in this case carbon black, then we have suddenly electrical conductivity, and we call this the percolation. And if we now go away from carbon black, which are rather large micro-sized particles, to carbon nanotubes, then we see here a result of carbon nanotubes. Just changing to carbon nanotubes, the percolation threshold level drops from, in this case, 0.9% to 0.04 volume percent. We can further work on that with the more modern carbon nanotubes. And here's something that we call here the single wall nanotubes, very thin, very high electrical conductivity. And we add them to the epoxy with a filler content, which is extremely low. So in the 0.0 value, or it is here, then we have here again a further reduction in the percolation threshold. So that is interesting, and so that we can use this electric conductivity of the matrix also as an advantage in composite material. So that means this is now the reduction if we use carbon nanotube single wall, a further reduction from that we had before by a factor of 10. So that is the possibility. Now, just very simple applications. One is if we have, for instance, a forklifter. A forklifter you have in the logistic companies, and they move on a floor. But what happens is, because you have here wheels made of a polyurethane or rubber, and that means you get a static loading on the whole structure here, but you have to get rid of that. That means you have to have conductivity between the floor that has to be conductive and also with the wheels. So therefore, in these wheels you see here, that is polyurethane, you add carbon nanotubes, so they become electric conductive. The floor itself has a cover of, for instance, polyamide, again, containing carbon nanotubes, or also C fibers, carbon fibers, recycled carbon fibers, and then you have a conductivity and you can get rid of the conductivity. So that is one part of that, what you can show here. Here now, more a personal thing, I want to show electrical conductivity of this aerographite, the three-dimensional, very light in weight composite structure and three-dimensional structure. And you can see here again, if you have here the composite material and the conductivity and the content of aerographite inside, and then you can see if you have here, the red one is just the neat three-dimensional structure, no epoxy inside. With the epoxy inside, we have here this black line, and that means you have an increase in the conductivity, of course, with increasing a content of carbon black in the matrix. What you now can do with it, let's see, is that we have a material, and we can, due to the fact that it is conductive, you put electric current on it, the composite material, nanocomposite with aerographite, it heats up. You have an increase in the temperature, and then you can just hold the temperature. So you have then here, it increases because you have here an electric path. You hold the current flow. What happens is overheated. Due to the overheating, it expands. The contact points here are interrupted. It cools down, and then again, you just wait. It cools down. Contacts are again, and it heats up again. And that can be used just here as an example, for instance, for a de-icing test on a wind turbine wing demonstrator, where you see here the demonstrator from the wind turbine blade. We have patched here to the at the inside the heating system, so that means the epoxy with the aerographite inside, and then you can see it heats up and the ice falls down and it can be removed. So that is something, similar results have been done also with carbon nanotubes using for the heating system as well. As it is electric conductive, you can use that also to sense either damage or also the load of a composite material. Again, here the figure which you know, you have here your nanoparticles in the matrix. It is electrically conductive, and therefore you can use this as an advantage. So here on a test coupon, it is shown. We have here a test coupon with carbon nanotubes in the matrix, in this case, glass fibers, which are not conductive, but the matrix is, due to the addition of carbon nanotubes, electric conductive. And then we strain, we load this test coupon. It elongates, as we can see. This is a stress strain curve. And if we look now to the variation in the electrical conductivity, then we can see here that the electrical conductivity decrease, respectively, the resistance increase follows the stress strain curve. So that you can use that, for instance, for monitoring in a static test. You can use that as well for monitoring damage, for instance, in a fatigue test. Here again, the glass fiber composite, 0.3% multiple wall carbon nanotubes in the matrix. It is electrically conductive, and we have plotted here the resistivity increase versus the number of load cycles, and as well the dynamic modulus. So that means the degradation and the decrease of the modulus of the material. And then you can see here, once we have a decrease in the modulus of the material, there is a damage here somehow. And that damage can be seen as well here in resistance change. In case there is a stronger damage in the matrix, then immediately you see also a jump of the electrical resistivity. So that means the electrical current capability of the matrix can be used to sense damage, respectively strain. Another thing one can use now, and I go back here for a moment from the fiber reinforced composites, just back again to the neat matrix system with the addition of carbon nanotubes. And we have plotted here, as we already know now, the increase in the resistivity with the strain. This is the test curve, and what you can see here is this line. It's nearly a straight line. So that means we have a very good and very high K factor, and over a quite wide range of strain. And if we look and now what happens here, again, just schematically, so we load it, and that means the distribution of the nanomaterial in the solid epoxy is somehow changes with the strain and deformation of the matrix, of course. So this gives us a possibility to measure an increasing resistance, partly to the fact that, for instance, these contact points, they are further away, and that increases the resistivity. So one can produce from this type of material, let's say, a strain sensing patch, and you can add something more into it so that there is a capacitance monitoring and so on possible. So we can use this now, and we add this strain or stress measurement capability on a composite part. You see here a glass epoxy composite part. It reflects somehow a beam of a wind turbine blade, and then I'll show that later. Then this part moves. What we can see here, we have different channels where we move that, and then you can see if it is on the upper part here that are these curves, the red and the green one, then you see once it is loaded, you have an increase in the resistance because it's strained. Or if you have follow the black one, that is the lower part, you have a decrease in the resistance because it's compressed there. And so then, you mean that is the result or the outcome from this? And now you can see how this beam moves. So that means here you see the capability of the data reinforcement of measuring stress or strain in a composite. So that means sensing of damage and strain during operation could also become possible by that, so that you test, for instance, glass fiber reinforced wind turbine blades while they are in use. Okay, this is somehow the end of my presentation. As I said to you, I'm from the Technical University in Hamburg, and I'm emeritus professor of the Institute of Composite Materials. My successor is Bodo Fiedler now. Most of the audience, I think, know him as well. And all the work which I introduced to you was funded by the German Science Foundation, was partly funded by the city of Hamburg, which is also a federal state in Germany. It was funded by the European Commission through the graphene flagship. Through the graphene flagship. Okay, that is brings me to the end of my talk. I'm prepared for some discussion and are waiting for questions. Thank you very much indeed.
Professor Schulte, thank you very much. On behalf of the organizers and all the audience, I thank you very much. And I'll be asking questions from the audience. So for those who would like to ask a question, please go ahead and enter it into the Q&A box you'll see in the lower portion of your screen. And I will compile and ask these questions to Professor Schulte. So we'll begin here. And I will say, one of the people specifically wrote in, thank you very much. Professor Schulte, thank you for the presentation. But I will begin with the first question, which is, how is the distribution of the carbon nanotubes controlled in the manufacturing process?
Okay, there are various possibilities to control that. First of all, it can be done by sonication. What we prefer to do is doing that with a so-called three-roll mill. And with a three-roll mill, that is can be changed into a continuous process. And that you have 3 rolls, and you have maybe already distributed via steering the nanomaterials in the matrix, but you have them finely distributed, and that to a great extent, we think the best process is using the 3-roll mill.
Thank you. With the addition of the nanotubes and other fillers, someone asked, can we expect a modification of the tribological properties due to the use of the...
Yes, yeah. Yes. The question is very good, especially you get that already with the carbon nanotubes. It's even better if you have graphene, and there I would say you do not need really to go to the graphene, which means just with the one layer. Maybe it's with the thermally reduced graphene, then you have there maybe it's a graphite type, but not very thick, and you have just the number of 10 to 20 graphene layers in it, and that gives very good tribological properties.
Thank you. There have been a couple of questions about the effect on viscosity, and then the implications into processing, processability, and manufacturing. Can you comment on that?
Okay, yes, that's a very good and very important question. And as we're just from the beginning, as far as I can see, Véronique Michaud, I think she will make a presentation in about 2 weeks. I do not know if she will cover this subject, because she will talk about, as far as I remember, on infiltration in composite materials of the matrix, infiltration into a fiber reinforced material. Indeed, the viscosity is a problem, because if you add these nanomaterials, the viscosity increases extremely. And therefore, you need to find new ways of infiltration. So it's difficult to do that just via resin transfer molding. That can be a process. So, but I think it's a whole story to explain that. The answer is it is a problem. We have in general solved it. In the moment, I see quite a number of progress in this field from people using and improving the various types of resin transfer molding techniques for adding this in between the fibers. It can be, for instance, one is that you use 2 rolls, And if you have a textile, then you, through the gap of the rolls, you move your textile, and on either side, for instance, you have the resin, which you have with a formally fine distributed nanoparticles in the matrix. And so that is also one way to fill that. But it is a problem. You have to be very careful with that.
There are a couple of questions following along that in some sense, asking about the status and perspective of commercial applications and other structural applications. If you could talk to scaling this up to commercial and structural applications.
Yes, a structural application. I said that there I see that it is used in ice hockey clubs. It is used for helmets, for instance, and then there are others which I do not oversee. There are very special applications normally, because the process is not as easy. And if you have a product which is really cost driven, then you have to find a compromise. So when we speak about carbon fiber and nanoparticles in the matrix.
What do you see as being the next steps and kind of a future vision going forward for the further adoption of nanofilled materials, nanofilled composites?
Okay, another composites, I think there will be a market just for using the electric properties of it. So then I see there's some, yeah, that means where you don't need much material. So it's mainly on the graphene or graphite, respectively, for the three-dimensional graphitic structures. I have examples where you use them for sensing, gas sensing. And if you do gas sensing with it, then you can use tiny things. You could add it to a smartphone, and with a smartphone you can sense then, so it's technology. From the technology possible, you can send down carbon dioxide and other gases. That would be possible, but then it's not a composite material. Then you just use the graphite or the graphite structure or the graphene.
Thank you. I'm going to summarize a few questions and try to ask them in one here. There's a number of questions about things like how can you tailor this or that or the other to achieve different properties. You've talked about thermal properties, electrical properties. So maybe taking a step back for people who are looking now to engineer with these materials and actually achieve some optimum balance between thermal, electrical, and mechanical properties. What tools would you say are available today? Where would you point people who are looking to do engineering and design work that take advantage of this new property space opened up by these materials?
Yeah. First of all, you can, in general, use the design tools already available. Of course, it is important to know if you want to have, for instance, an improvement in the fracture toughness. And if you need that, then there is a possibility to use that. For instance, there's one discussion, it's only also mainly on the scientific side, the so-called thin ply technology. And if you might recall that with the thin plies technology, failure of a composite is more brittle as that of a traditional composite material. If that is more brittle, that means, of course, it's not as damage tolerant. So that means I see there a good improvement if you use nano, mainly in this case, I would say a few layer graphene in the epoxy matrix for a thin layer fiber reinforced composite, and to improve the fracture toughness there. So I think I cannot give really a general idea of that. People have to see what is the application. They have to understand what are the matrix properties. Can I have an improvement from a matrix which has a higher fracture toughness? Can I have an improvement of a matrix which had a high, or improved electrical conductivity? I can have that. If I have carbon fibers and have a electrically conductive matrix, then in general, the electrical conductivity is better. And that can be good. I think it cannot be for the moment as good that, for instance, if you're an aircraft and you have a flashlight on it, that you can get rid of the electrical conductivity. You still need to have here the copper, what is it, the copper grade around it, but maybe. So there are things in the future where you can dream of, and sometimes dreams become true.
Thank you. Got a few fairly technical questions. Someone asking the question, you spoke about degradation in the presentation. Someone asking if you might clarify the definition of that degradation.
Okay, I try to do that due to the low time. Degradation would mean if you have, for instance, a variable loading in it, then you have something as a fatigue. And degradation means that you the properties in the composite are reduced due to the fact that with an increasing number of load cycles, you induce internal damage that can be crack, that can be delamination, and so on. And that leads to a reduced, let's say, generally a lower stability of the structure. And so the structure degrades in that sense. It's in the course of this presentation more related to cracks, delamination, fiber matrix debonding. It can be, of course, for instance, if you have a matrix and it picks up moisture, then the matrix will swell, the properties of the matrix are reduced, and also that has an influence. That is also could also be part of a degradation, but it's not that I used it here and discussed here.
Thank you. There's a question about do any of these particles or fillers improve vibration absorption in primary structural operation?
Oof. I say oof. I hesitate a little bit because I see two possibilities. I have no experience on it. One would be if we improve the stiffness, the modulus of the matrix, then it would have an influence on the vibration. It could be also that it is reduced. No, I cannot give that. It will have an influence, of course, but in which direction I can only speculate.
Okay. There's another question here about the conductivity over temperature characteristics, and do they correlate with the weight percentage of added carbon, or how would you adjust the behavior of the material to the desired turn-off or deactivation temperature?
Okay, first of all, if you the conductivity you can adjust with the amount of nanoparticles you add. You cannot achieve extremely high electrical conductivity in a nanocarbon epoxy material. So we have experience, I haven't shown that here, that we have carbon nanotubes with a length of 2.5 millimeters, and they are all nicely parallel to each other. And then we can achieve an electrical conductivity which is a little bit less of that of iron, somehow in that range. By the fact the carbon nanotubes themselves, they have an electrical conductivity that is maybe outperforms that of copper, but that you cannot achieve. So that means there's a wide range which you can achieve for the electrical conductivity. In parallel, somehow goes the thermal conductivity of a material. Of course, so that means the thermal, yeah. And of course, the electrical conductivity is always dependent on the temperature as well. And I don't know if the person who asked the question is more looking to the fact that we have this self steering of the temperature due to the extension of the matrix, and then we have conductivity, then it cools down, and then no extension, we have no conductivity and it cools down, then we have suddenly a conductivity. I don't know if he goes to that, but we have always things which are somehow parallel or interact with each other, temperature and also electrical conductivity and the amount of carbon nanomaterials in the matrix as well.
Thank you. Someone's asked if there are airborne hazards with carbon nanotubes, and if so, how to best work with them.
Carbon nanotubes themselves, there is some hazard. This is under investigation since 20 years. And it was shown that once just the nanoparticles, the carbon nanotubes, for instance, are airborne, then there can be inflation, can be shown inflation on biological species. And that means you have to be careful when using it. Once it is in a polymer, then it's covered and there is no problem with it. But while you handle it, while you put the carbon nanotubes into a matrix, you have to be careful so that they best do not get airborne. We had made in our lab some tests, and it was that we couldn't find airborne carbon. We tried to have this, that they are airborne. We couldn't have in the measure airborne find carbon nanotubes in the air because they are so small and light in weight. But we found them immediately on the surface of tables or parts. So that's a measure of the interaction and the electrical interaction between the carbon nanotubes and the parts. So can be hazard, no real danger, but you have to be careful while handling. And there are rules how to handle them.
Thank you. Someone asked a question about the piezoresistive behavior. They asked, what is the origin of the negative piezoresistive behavior in the nanofiller modified composites?
What do you mean with therefore a negative piezoresistance behavior? I have got that. So I have electrical conductivity.
Mm-hmm. Yeah, they have misinterpreted one of the results then.
I have to look that up. I cannot be just standing here a proper answer. The negative piezoresistive behavior. I need a discussion with him.
Yeah. And what we'll do is we'll actually pass along the questions to you, and you can feel free to reach out to these people.
Yeah. Great. Thank you.
Yep. There were some questions about fracture and failure and cracking. And so one was, do the cracks start inside the filled matrix or along the fiber matrix interface?
Okay, that depends always on the fiber direction. and that means on how the composite is loaded. Normally, it is in the matrix in between fibers, so it's a transverse crack between fibers. Then there can be, if you have high shear stresses, then as well, okay, there can be cracks in the matrix alongside the fibers or in the fiber matrix interface. So that depends on the load situation, orientation of the fiber, and it depends also if you have, let's say, an area where we have a concentration of matrix. Then this can be the initiation point for cracks. For instance, if you have a textile, then in textile you have in between, you have not an even distribution of the matrix. And if you use nano-reinforced matrix as well, it's not even distributed due to the textile and weaving or other structures, knitting structures.
Thank you. There's a question about the effect on the glass transition temperature. So do the nanotubes affect the glass transition temperature value and also the operational temperature?
They do have an effect of the glass transition temperature. And in general, there is a reduction, a small reduction in the glass transition temperature.
Mm-hmm. That can be tuned as well.
So I cannot give numbers now. I don't have that. Then I also have to go back into some literature.
Mm-hmm. There was a question about carbon nanotubes or graphene. Which would be easier to control in terms of controlling the final orientation while manufacturing?
So if you have the final orientation, then maybe the carbon nanotubes is easier to control. However, the graphene and graphite, it depends always on shearing of the matrix during the preparation of the nanocomposite, and but that is not as easy, I think, to control. But it depends on the shearing behavior in this nano level. Then they will orientate alongside this shear direction. But with the nanotubes, if they are long enough, it's easier as with the graphene. But yeah, I would say so. But both is possible.
Lastly, there's a question here about asking about your thoughts and experience with the challenges or disadvantages or things to be mindful of when you're processing and applying these nano modified composites. Are there concluding remarks you'd give about things for people to be aware of as they begin to work in this area, things that perhaps they should be mindful of that might be different or beyond what a composites processing group might be used to dealing with?
Yeah, I have to think about it. Have not really got the point of the question. So if maybe it's meant that if one is starting to research in nanocomposite materials,
Mm-hmm.
if he can be in front of the train or he just follows the train. I would say there's still lots of room for properties and improving properties. Mainly, I think it's not only in these type of properties. There are others with glass fibers and so on. So I see there a room also with other nanoparticles in it, and they can have very specific properties. So first, I don't, you see, it's nanocomposite materials. It's a research performed since about 20 years. So that means there is quite a big success in it already, but still there's room for improvement. So a very general answer. I have something very special in mind. We work on that, but that's something we will see what comes out of it. Part of it I have said, for instance, with, thin ply technique, for instance, that is something where I see that.
Very good. Professor Schulte, again, we thank you very much for your presentation. We thank the audience for your participation and questions, and we'll look forward to further conversation on cdmhub.org, where these further can ask questions. Professor Schulte will email you this list of questions, and we'll look forward again in another month on March 31st to hearing from Professor Veronique Michaud from.
Okay, I thank you as well, and for giving me the chance to have this presentation. So thank you.
Again, thank you very much. Thank you all.